Hey guys, here we go. Second attempt of the day. Hopefully this time we'll get through, get to the other end, and actually upload something this time. Okay? So, what we're going to do is we're going to go for some integration of exponentials and logarithms. Okay? We're going to start off by recapping what we learn in terms of the differentiation, because it's been a little while. Want to make sure that we cover these things properly. And what we're going to do is, when we've covered the differentiation, we're going to look at how we can use some of the ideas from the differentiation to possibly help us with the integration. We're going to remind ourselves of from some AS level integration rules as well, so that we can pull together all of these things, figure out how integration of exponentials and logarithms work. If you've got some pen and paper, you can follow these things as we go. Feel free to pause as we do them, and if you want to have a go at some of the questions before I start going through them, again, feel free to pause the video at any point and then to go from there. Okay? And without further ado, let's get kicking. So, a little bit of a reminder about differentiation first of all, okay? In our previous video, we learned what the derivative of an exponential function is, okay? And just from the definition of what an exponential is, the derivative of an exponential is that same exponential, okay? So d by dx of e to the x is just e to the x. Okay, it's just as simple as that. The rate at which it increases is proportional to its value at that point. Okay. So we also looked at what happens if we had some kind of a function as that power. Okay, and you might think to yourself now, okay, I kind of remember how to do this. We still have that function as part of our derivative, so we're still going to have e to the 2x as part of that, but we're going to have some kind of multiple of this. Okay, so just have a think to yourself, can you remember what that multiple will be? What would we put in front of this e to the 2x for our derivative? Okay, so for this thing here, what we actually put down is a 2. Now, how do we know that that's going to be a 2? It's because it is the derivative of the power. Okay, if I take that power there and I find d by dx of that power, I get the coefficient, or what goes in front of that e to the 2x that we started with. Okay? Now we've got a little bit of a variable change here. D by dt, so it just means differentiate with respect to t, pretend that t is the letter that we're differentiating. And I've got e to the at plus b. So we've gone full algebra, okay? A and b are just constants, they're just numbers, okay? So we know what one part of this has got to be. We know that one part of this has got to be e to the at plus b. The question is, what goes in front of that function? Okay, what goes in front of that? So I'm just going to give you 30 seconds to think about that. What should go in front of that function? And while we do that, I'm just going to get a little timer ready to, just in case I need it, because I've got a feeling that I used it earlier. Perfect. Okay, so what goes in front of that? The derivative of our power. Now, differentiating at plus b with respect to t is just going to be a. Let me draw. There we go, a. So the derivative of this is just a e to the at plus b. Okay. Now, we got one more before we get to our general rule. We've got d by dx of e to the ax squared plus bx. Okay, this one's a little bit more complicated, okay, but let's follow what we've done so far. we know that it's going to be proportional to the original function. So I know that it's going to have something which includes e to the ax squared plus bx. What goes in front of that exponential is the derivative of the power. Just going to give myself some brackets ready. So what is this thing when we differentiate with respect to x? Have a think for yourself. Well, we're going to get 2a to the 2ax, because the power decreases by 1, plus b. So the general rule of all of this, what this all boils down to, is if we have the derivative of an exponential with some kind of a function as its power, what we get is the derivative of the power and a repeat of the original function. Okay, that's what we get. So that's a little reminder to do with the exponential side of things. Okay. When it comes to the logarithm side of things as well, when we do the differential of a logarithm, what we get to start off with is just 1 over whatever's inside that logarithm. Okay? But it was actually a little bit more than that. Okay, we discovered that actually that there's more to it than just 1 over what's inside that logarithm. And that came about when we started looking at this sort of stuff. So if we got the derivative of ln of 4 of x, 4x even, what we actually had was something over 4x, but what was that something? Well, that something is the derivative of the function that's inside the ln brackets, this thing. So the derivative of 4x, which is just 4, that gets us what we have to start off with, but then it simplifies to 1 over x. Okay? Having that step in the middle will be important for when we deal with more complex functions, but in terms of, going from this thing straight to that thing, we can do that. Okay? Now for this function here, you might want to have a think about this one yourself, okay? I'm going to give you 30 seconds just to have that's 3 minutes, and I'm going to give you 3 minutes. 30 seconds just to have a think. What would that differentiate to? What happened with our original functions? What happened with the two that we had before? What did they become? Have a look at the similar example that we've got for our exponential. Could that help us? What are we going to get when we differentiate ln ax plus b? Well, what we're going to get, we're going to find out now. So what we're going to get is we're going to get a function. This doesn't happen again. We're going to have a function with ax plus b underneath as our denominator. And we're also going to have the derivative of that up top. So the derivative of ax plus b is going to be a. Okay. Now, this is why this step that we did here is actually important, because this doesn't cancel down to just being 1 over x. Okay. Because we've got that plus b part of things as well. Okay, I can't just divide the a's by themselves. Okay, that stays as it is. So our generalized rule, if we're differentiating a logarithmic function, and it's got a function inside of it, what we get is that function as the denominator and its derivative as the numerator. Okay, now those two things that we have there, which I'm going to just put a circle around in purple. So this thing here and this thing here, those are our what we'd call the general rules. Okay, we need to be really on top of how we need to be on top on remembering those, essentially. Okay, I'm not going to beat around the bush. We need to know those things. Okay, we need to know how a logarithm differentiates. We need to know how an exponential differentiates as well. But this is all a recap. Okay, that we have looked at this before. Okay, what we want to look at is the integration. Okay, now with the integration, we're just going to remind ourselves of two key things before we actually tackle any integration problems. The first thing that we're going to remind ourselves of is this rule to do with constants multiplied by a function. Okay? So if we have an integral of a number times a function, what we've got here, a is just like a real number or a a fraction, something like that, any of those two things. What we can do is we can actually take that number outside of the integral. It has no impact on what the function actually integrates to. Okay, so if we have a number times by a function, we can remove the number from the integral, even if that number is a fraction, an integer, a decimal, whatever, and we can just integrate the function by itself. And we can also do that with differentiation. We can take the number outside of the derivative and just differentiate the function. That's the reason why if we, differentiate, 3x squared, that's the same as us doing 3 lots of the derivative of x squared. 3 lots of 2x, which is 6x. Okay? It's something which we may be taking for granted right now, but is important. Okay? We're going to see why later. Okay? And I'll come back to this when we get there. So, integrating exponentials. When we differentiated an exponential, we got the same exponential function. Okay? So if we were to integrate both sides of this, what would happen is I would effectively be cancelling out the derivative. Okay, integration is like the opposite process to derivatives. Okay, so you could imagine those two things cancelling out. So what we'd be left with is the integral of e to the x is equal to e to the x. Okay, and that makes sense because if we differentiate an exponential function, we get the exponential function again. So if we do the opposite, if we do the reverse, it should just give us what we started with, which is the exponential function. Okay? So that by itself is not correct. We're missing something, as with all integrations with no limits. We have to remember that constant of integration, okay? We have to remember it. Now, for this next one, we're going to jump back to thinking about the derivative of e to the 2x. Okay, now just as a reminder, d by dx of e to the 2x, what was that? Have a think to yourself now. Don't look at your notes. Have a think. What was d by dx of e to the 2x? Can you work it out? Two e to the 2x? We're good. Okay. Now, if I integrate both sides of this, the integral and the derivative would cancel out. Okay. So the integral of 2e to the 2x would be equal to e to the 2x, but that's not quite what I want. It's close, but it's not quite there. Okay. Instead, if I take that factor of a 2 outside of the integral, doing what we can do here from our previous slide, excuse me, what we can say is that e to the 2x is equal to 1/2. Oh, sorry. No, it's not equal to 1/2. I'm getting one stage ahead of myself. Okay, you might be able to now figure out what the answer should be, but I'm going to carry on. Is equal to 2 lots of the integral of e to the 2x. So what does that mean? That means that the integral of e to the 2x is 1/2 e to the 2x. Now, sir, if I have to go around doing integrals of both sides to things, knowing what the differentials are and everything like that, this could be quite the headache. Yes, I say, I mean, it could be better for sure. So let's have a think. When we differentiated e to the 2x down here in red, we got 2e to the 2x. We multiplied by the derivative of the power. Can you tell me a quick way for me to get this answer from here? Can you tell me a quick way for me to get from this, integrate e to the 2x, to an answer which says 1/2 e to the 2x? Just have a think. Well, the short answer is that we've taken our power, differentiated it, and then divided by it. Yeah? Derivative of 2x is 2. Dividing by that, 1/2, or half of e to the 2x. So that means now we can actually do the rest of these integrals a little bit quicker. At least hopefully. E to the ax, a, let's just say, is a real number. Okay, it's just a normal number. E to the ax, following the pattern that we've got here, should be 1/a e to the ax. Or you could write that as e to the ax over a. Okay? There we go. But I've forgotten something. Plus our constant of integration. We've got it there as well. We were so caught up in discovering shorthands for doing exponential integration that we forgot our constant of integration. We can't forget it. It's important. Okay? Now, bit more of an awkward exponential. Exponentials with all sorts of things going on in there. Okay, so let's have a look at what we've established so far. We've established that we're going to have some form of the original function involved in our answer. So I know that some part of this is going to say e to the x squared plus 3x plus a constant of integration. The question is, what are we going to be timesing by? Or in this case, maybe the more question would be what's going to be on the bottom of our fraction? What's going to be the denominator to this? Let's give you 30 seconds to think, okay? How are we going to finish off that integral? And if you are already there, you might want to think, can you establish a general rule? Can you write a general rule for the one underneath? All right, so what we're actually going to get is the derivative of the power, okay? Now, the derivative of this power is going to be 2x plus 3, okay? Now, if we were to take this thing here, and if we were to differentiate this thing, what we should get is this. What we originally started with inside that integral, okay? And it turns out that that does work, okay? If we were to differentiate this, we would differentiate the power, multiply by that, which would cancel out this fraction. The constant of integration would vanish because constants differentiate to 0. And there we go, we'd be left with e to the x squared plus 3x. But the general rule, the one that we've got left, e to the f of x. What is the general rule? How can we establish a general rule for integrating any exponential function? Well, what we've done is we've taken 1 over the derivative of the power times by the exponential function, and then added a constant of integration. Happy days. Okay. There we go. That's integration of exponentials. Okay. Now, what we will need to be able to do is we'll need to be able to use this. Okay. When we come to doing differential equations, especially second order differential equations in Core Pure 2, we're going to be using hang on, let me get my laser pointer. There we go. We're going to be using this a lot. Okay. And when you come to some of the mathematical methods things that you will do as well as some of the things that you'd look at university level maths, being able to quickly recognize exponential integration solutions is actually really nice and really helpful. Okay, so that wonderful little thing there is going to be one thing that we're going to look to commit to memory. Okay, and the quicker that you can spot it, the more fluent you'll be as a further mathematician or as an A-level mathematician. Okay, so we've got one more thing to do. Okay, I realise that I'm doing this a little bit quicker than I did it first time round, and it's probably because I've already done it once today. Okay, so if I am going a little bit quickly, feel free to put questions together, slap them into an email, and then send them my way. I'm more than happy to answer your questions from there. Or if you say, I didn't really get this, could you do like a couple more examples for me or find a different resource for me? I'm more than happy to help you with that, okay? So, logarithms, okay? This is where things are going to get equally as interesting, okay? So, this is what we've established so far. Okay, and I've put in brackets the general form of it so that if we were thinking about any kind of function, okay, the derivative of a logarithm is the original function inside the logarithm, and then the numerator is the derivative of that original function. Okay. And what we can do is we can use a similar kind of logic to what we did before to figure out what some of our integrals will be. And there's going to be a little bit of a, what's the word? Not distraction. digression, that's the word. There's going to be a little bit of a digression as to explaining some things, which we'll do about halfway through this slide. Okay. So, if differentiating ln of x gives us 1 over x, integrating 1 over x should give us, fill in the gap. Correct, ln of x, okay? Now, we don't just put ln bracket x. That is not right, okay? What we put instead is ln mod x. Straight lines, okay? We want to return the absolute value of x, okay? And there are some graphical explanations of that which are pretty good, but I don't want to take too much of a digression out from the actual integration of these things. If you want to know more about that, it'll either get explained in your A-level class when you get to it yourself, or you can ask and I will send you forward some resources that explain that quite well and show it quite neatly as well. What have I forgotten? My constant of integration. Okay. No limits in my integral. Need a constant of integration. Now, this is where we're going to have one of two different explanations of what we'll do. Okay. We're going to have one explanation which is going to be using the information that we've got on this slide here. And we're going to do that first because I think that that is a really quick, a really efficient way of doing it. Okay, so remember, if we got a constant times a function, we can take the constant outside of the integral. Now, 1 over 2x, that can be split up into two different things. What can that be split up into? I'll give you a clue. It's a fraction times by another fraction. Now, if you're saying to me that the numerators have both got to be 1, you're thinking of the right things, because 1 times 1 gives us 1. And if you're thinking as well that 2 times x gives you 2x, well, there you go. And here we've got a constant times a function of x. So what this is effectively giving us is it's saying a half of the integral of 1 over x, which we know what that is. That is half ln x plus c. Okay, so that's going to be half ln mod x plus c. Now you might be saying to me, but hold on, Mr. Hughes, hold on. That says a half of the integral. Now the integral itself gives you a constant of integration. Why have you not written a half times the constant of integration as well? That is a fantastic question. It's because if you take a constant and you times it by another constant, what do you get? You get just another constant. It's like saying if you take 2 times 3, you get 6. And both of those things don't change with, like, your changing value of x. They are constant. They're just a number. Okay? So I can forego the doing a half times c and writing it as c over 2, and I can just write it as a new constant. Okay? It's a great way of being lazy. Okay? The constant of integration mostly takes care of itself. Okay? Now, we may have to work around with things in order to get it in a format that we can recognize that what we've actually got is a logarithm. Okay? Here, I didn't check about the top being the differential of the bottom. I didn't check that. All I did was take the constant out and then go, oh, hang on, I recognize that, slap that in, done. Okay. What I'm going to do here is doing a second method for looking at this, which is checking to see if the derivative of the bottom is the top and adjusting for it if I need to. So let's do this. The integral of 2x to the power of negative 1. Let's write it as a fraction first. So it's the same question as we were dealing with before. Okay. Now, we know that if I differentiate the bottom, in order for it to be a logarithm, I would have to get the top. Differentiate the bottom, get the top. Okay? But it doesn't quite work. Now, if I differentiated 2x, I get 2, not 1. It's like saying I've got 2, I want 1. What am I going to have to do? Well, looking at the answer that we've got from above, you might be quite quick to say, well, if I've got 2 and I want 1, I've got to half it. And you would be 100% right. Okay. So what I'm going to do here is instead of saying, okay, I'm going to get, what I would get is 2 over 2x. I'm just going to do half. That's not the same blue. Can't do that. It's not on. There we go. Is I'm going to have a half ln 2x plus c. Now, hold on, Mr. Hughes, you're going to say. You're going to say, oh, for God's sake, stop saying now, hold on, Mr. Hughes. But hang on a minute. There can't be right. That can't be right. We've got two different answers. What are you talking about? Now, are they two different answers? Well, yes, they are. Can we make them so that they're the same answer? Yes, we can. Now, if you know your laws of logs, I'm going to do this in green, okay? If you know your laws of logs, you know that ln of two different things multiplied together is equal to the ln of those two things added together. Ln of AB is equal to ln A plus ln B. Okay, so we could split this up into a half ln of 2 plus ln of x. Okay, now I'm going to get a little bit ropey for room here, so we're going to see how we do. Now, from here, the ln x part of that function, that's something that varies. That's something that will change as x changes. Ln 2, that is a constant. That is always going to be the same number. Ln 2 is just going to be a number, whatever that is. I don't know. Okay. So if I do half of ln 2, that will be a constant. It's just going to be a number. Now, if I have half ln 2, which is just a number, and I add another number, that will get me a third and final number, which is just another constant. Okay? So actually, taking a half ln 2x plus c and having it equal to a half ln x plus c, as we got from up here, we can say that these two things will be equal provided that their constants are different. Okay? So the constants here will be different. Okay, we've used the same letter, which is bad terminology. That's poor terminology on my part. But if I was to change this from C to D, for instance, and actually make it obvious that they are two different constants, we will be talking about the same integral. Okay, now if you're saying to me, well, which one do I go for? I've got two potential different answers or different looking answers for the same thing. My instinct is always it doesn't matter. It can always work itself out in the end. The constant of integration will take care of itself. Okay? It generally doesn't matter. Okay? Now, in terms of the working out, my personal opinion is that I think that this one is slightly easier. Especially for slightly easier functions like this. Okay? However, for some other things as well, we may need to bear this kind of alternate method in mind. Okay? This is, for me, I think that this is easier by taking constant terms out of the integral. But this may also have its place. Okay? Now, what I would like to happen from here, no, let's go back to blue, is that I would like you to take just a minute while I have a drink, because I've been talking for nearly 35 minutes straight, which is a long time. I'm going to take 2 minutes for you to have a think about the next integral on our list. 2x to the negative 1. I'd like you to rewrite it so it becomes a fraction and think about how would you perform that integral. Okay, I'm going to go get a drink and I'll come back and we'll answer that question together. Okay, I'm back. We're doing 30 seconds to go. I may have had a bourbon as well. Okay, so we're thinking about this. Just in case, what that should be is 2 over x. Okay, and I realise that we're a little bit early on the timer, but there it goes. Okay, so 2 over x. 2 is a constant term. We can split this up so that it is the integral of 2 times 1 over x, which is just going to be 2 lots of the integral of 1 over x. Now we know what the integral for 1 over x is, so this is going to be 2 lots of ln mod x plus c. Happy days! And we could do the question the way that we did the one previously, the one down here, but I hope you'll agree with me that doing it this way is actually quite quick and quite nice. Okay. Now this one, if I were to just do a quick check, the bottom, if I differentiated the bottom, I would need a scale multiple to get the top. Okay, so we do have a logarithmic function. That's fine. Okay, now this I'm going to do 2 steps in one. We're going to have 3 over 2 lots of 1 over x. So when I when I integrate this, I'm going to have 3 over 2 lots of ln mod x plus our constant of integration. Okay? Apologies, just taking a drink. Now, we will need to check really carefully as to making sure that we get a derivative which is the numerator of the fraction, and the original function is the denominator. Okay, so let's look carefully at this one. Is the numerator the derivative of the denominator, possibly multiplied by some number? And look carefully. No, should be the answer. Okay, because if I were to just take this down here for a second, if I were to differentiate x squared plus 2, x squared plus x, sorry, what I'd get is 2x plus 1. Now, I cannot times this thing by any one number in order to get the numerator of that fraction. Okay? So this integral does not become a logarithm. Okay? Because there's no one single thing that we can times by to make the numerator the derivative of the denominator. Okay, so as it is, this is not a ln thing. It's not one. Okay. Now, there are other things that we could do with this integral, but that's beyond the scope of this video. Okay. However, we can change this so that it is a question that we could do. Okay. So what I'm going to do is I'm going to erase the ink that I've got there. If you want that, you're going to have to just rewind it and pause it for a second. I'm going to erase this down here as well. Okay. And what we're going to change this question to is we're going to change this to 4x plus 2. Now, you remember all those times when we're dealing with algebraic fractions at GCSE and or dealing with quadratics at GCSE, and we said for you to look for common factors. This is going to be important here as well. But what we don't want to do is we don't want to be factorizing out any of our variable. What we want to be doing is factorizing out constant terms, just to be making it as simple as possible. Okay, so what's a constant term that I could factor out from this? Well done, 2. So what I've actually got for this top bracket, or for this top part of our fraction, is 2 lots of 2x plus 1. Okay, now if we use that and take out the constant term of our integral, so we're going to take 2 outside of our integral, we're going to have 2 lots of 2x plus 1 over x squared plus x. Now, is that a logarithmic? If we integrate that, will that become a logarithm? Yes, because when we do the derivative of the denominator, we get the numerator. Happy days. So what we're going to get is 2 lots of ln. What goes inside of the mod sign is the denominator. So x squared plus x plus the constant of integration. And finally, general rule, integral of the derivative over the original function, we're just going to get ln mod f of x plus c. Okay. And there we go. That's us dealing with integrals of logarithmic functions. Okay. Now, there was something that I did have up originally, which I don't have up right now, which I'm just getting, so I'm stalling for time. Stalling for time. There we go. Okay. And these are the key things that we're looking to take away from today. Okay. We're looking to take away that if we integrate an exponential function, we get 1 over the derivative of the power, the original exponential function as we had it, plus a constant of integration. And if we have the derivative, the derivative on top of the original function, that becomes a logarithm plus our constant of integration. Now, if I click this button, hey, there we go. Now, this is a slightly older worksheet from when before things started to change with regards to things turning into core pure and pure 1, pure 2 and things like that. It's from the old A level, but it's still a perfectly good worksheet for dealing with integrating exponential and logarithmic functions. Okay. The worksheet itself can be found in full if you go to physics and maths tutor and you go to the maths part. I think actually it would be really useful here if I put up my right screen. Whoa, what is going on? There we go. So yeah, if you go to physics and maths tutor, if you go to maths revision and you go to core 4, which is this one down here, and you go to Solomon worksheets, the worksheet that I've got up here is integration A. Okay, you can see that this thing here is the same worksheet as I've got behind. Okay, and you'll be able to have a decent go at pretty much all of these, and it's got some application of it as well. They're actually really good worksheets. Okay, with the added bonus of if you go one step behind and you go to integration A, they actually have the answers as well. So perfect for doing some kind of revision or practice like we've got now. Okay. So what I'd recommend is trying out a few of these. And if you want to send me a photo of solutions, if you want me to check them, that's fine. If you want to check them yourself, that's also fine. I'm also aware that we've already sent you some work for this week. I would think it would be great if you can do this, that if you find yourself overwhelmed with other things, it's not the end of the world if this doesn't happen. Remember, you will see this again at some other point. Okay? So, second time round for this video for me today. And it didn't get any shorter. We have now capped at about 50 minutes, give or take 9 seconds. So I'm going to take 5 seconds now just to say I hope this video is useful. I'll see you hopefully very shortly. Take care. Stay safe.